Shall we start? Okay. Okay. So let us. We have been discussing in the last class the various aspects of protein dynamics. We talked about the relaxation mechanisms in some sense, the T1, T2s, and how these are affected by the dynamics in the system. We said the dynamics is intrinsic to NMR, and naturally we will extract different motional characteristics from the NMR data. Different kinds of dynamics exist in protein systems at various time scales from picoseconds onwards up to seconds. And these are these represent different kinds of motions inside the protein chains. There may be small vector motions, or there can be loop orientations, and there can be exchange mechanisms and things like that. And so we stopped at the chemical exchange phenomena. How does it affect the NMR spectra? How does it reflect in the NMR spectral features? And we are continuing from there to obtain more accurate information about the exchange mechanisms, exchange phenomena occurring inside protein systems. And this is best studied in a quantifiable manner by what are called as relaxation dispersion experiments. These are R2 based experiments. And we all know the basic scheme here of T2 measurement. This is a spin echo sequence. So we have the spin echo here, 90x tau, 180x tau echo. The echo amplitude is proportional to exponentially is e to the minus 2 tau into R2. R2 is 1 by T2. And that is if there is no diffusion in the system, and we have, this is a simple sequence, the tau and tau are equal. So when you are doing an experiment with small tau, it is fine, but then suppose the tau is not small, then what can happen is that the chemical shift frequency present here, and if the frequency present here are not the same, then it will lead to kind of a not proper refocusing of the chemical shifts, and then the echo amplitude will be affected by the chemical shift differences because of the diffusion of the molecule. When you say diffusion, what do I mean? So if I have a sample here, so we have the solution, the portion from here and here. If the molecule diffuses from here to here, and the magnetic field is different in these two places, then if in the first tau it is here, and the second tau if it is here, first tau it is here, the second tau if it is here, then there will be not proper refocusing, and that can also affect the echo amplitude. And in such a situation, the R2 which will measure will not be accurate. If it is assumed that it is the same, then of course it will be entirely, homogeneity will be refocused, and you will have the proper T2 measurement, R2 measurement there. The other thing that also affects is the chemical exchange. Chemical exchange, what is chemical exchange there? So a particular system is undergoing chemical exchange between two frequencies, A and B. If I have a chemical shift here, represented by the frequency omega A, and this has a frequency omega B, and during the first tau period, if the frequency is omega A, and in the second tau period, the frequency becomes omega B, then of course it will also not refocus here, and the T2 you will measure is not going to be precise T2. And that influences the R2 measure. So we call that R2 value as R2 effective. Chemical exchange during T2 tau influences the measured echo amplitude, and then when you try to fit this to an exponential, you will get an R2 value, all right, but then it is not the true T2, or it's not the true R2, it is so-called effective R2. And that is called as, this is chemically expressed here a little bit in more detail. So you have a situation like this. Consider this A and B is exchanging between two sites A and B. Of course, the populations of the two are not the same. One of them is 99%, the one is 1% or whatever. Then it is exchanging between two sites. And what is the sort of an exchange we are talking about? Here you see, here you have the A state. This is a folded one here, the protein. And if it is in the B state, there is somewhat unfolded here. The chemical shifts, the frequency of precision at this point may be different from the frequency of precision at this point. And the nitrogen frequencies, if you are measuring, then it will have different peak positions there. So therefore, they have different chemical shifts. So in such a situation, if you measure the using one of these peaks, which is the major peak, because you are going to see that major peak, that is the small peak may not be visible to you, but you see the major peak here, then incomplete refocusing of the chemical shifts because of the exchange phenomena, it will cause a reduction in the R2, reduction in the peak height. If it causes the reduction in the peak height, what it means, then of course you have R exchange contribution to your the line gets broadened, therefore the measured R2 value will not be precise. So therefore what one should do? So similar to what this Karpusel did to get rid of the diffusion based echo modulations, you do as a similar trick here, that you, instead of applying a single line 180-degree pulse in the middle of the echo, you apply a series of 180-degree pulses as indicated down here. So that means that in between every echo, it happens very quickly. So if you apply lots of echo, the decay here, then the refocuses, then the decay here, the refocusing, decay here, refocusing, and things like that, it happens very quickly, then the chance for the chemical shift change is reduced. The chemical exchange effects will not affect the echo amplitude at every point in time, because then every time it is refocused. So therefore that will not happen, and then what you will measure will be a complete refocusing of the thing, then you see the peak height will go up. So therefore, if you measure, so what does it depend upon? It depends upon the time which you give between these for each of these. How much is the time here? How much is the time here? Like that. How much time you give between the 280-degree pulses? Okay, that is called as a particular tau. This one, and the inverse of that is called as the frequency. New CPMG. Corpuscle mapping, it is the same trick. You use the frequency is called, that's called the frequency. Inverse of this time is called as the frequency. So how you apply this series of pulses there, and you will therefore eliminate the effects of changes in the chemical shifts due to either the diffusion or due to the chemical exchange phenomena, and you can do the experiment as a function of this frequency. So you do several experiments depending upon the varying the value of CPMG, and you will see here a curve which is like this. You measure the R2 at every value of the frequency. Okay, so when the value of the frequency is very small, suppose for example here, if I have at this point, that means if the frequency is small, meaning what? The time gap between the two, this ones is very large. Okay, that means there is a scope for diffusion, there is a scope for chemical exchange, and then you will see a high R2 value as it is indicated here. So as you keep increasing this frequency, this starts going down. This R2 effective starts going down. Finally, it will reach a saturation value at some particular point, it flattens. That means after that, you don't need to increase the CPMG anymore. Once you reach this point, then you've already taken care of the artifacts due to the diffusion or due to the chemical exchange. Then whatever value you will measure here at this point will be the true R2. So this will indicate what is the contribution of chemical exchange to your R2 value. You have so at every point, if this is your R2, this is the intrinsic R2 what you have here, and if you have an R2 at this point, so this R2 minus this R2 gives you the chemical exchange contribution at every point. Okay, so that is how we can measure the chemical exchange contribution at this. It's an artifact, actually, an artifact of the experiment. So you will see that it is the chemical exchange is contributing there. Chemical exchange rate you are not going to measure here at this point, but you see, okay, there is an indication that exchange is contributing to your R2 value. So ultimately, for you want to measure the true R2, then you have to get this value. And to see whether there is exchange contribution to your R2 or not, you have to do this experiment for varying the new CPMG. Okay, and plot the R2 you measure. And for measuring R2, what you do? Any value of thing which you give, you do a series of experiments with varying tau and fit your data with exponential, right? So that is what you do here. By varying tau, you get an exponential decay of the echo amplitude, and then that is proportional to the from the one you fitted, you will get the R2 value. So you have to do this for every value of these kind of things. For every tau value, what you do? You have a series of these pulses. So and that determines the frequency. For every tau, you have series of this frequency, the new frequency, the new CPMG. So with every particular value of CPMG, you keeping the tau the same. Because you want to measure the R2 means you will have to have a series of tau values, right? So in order to get e to the minus 2 tau R2, so you have to do series of tau experiments, and then you will fit the data with that, you will get the R2 value. So to do that, you do a series of experiments. For every tau value, you use different CPMG. That means if the frequency is, let us say, 2, then you have 2 such sequences in that tau period. If it is 4, then you have 4 echo sequences in that tau period. So when you increase the tau, then this number will increase. Okay, so more and more number will repeat, and therefore you will measure the T12. So each of them point here is a separate R2 measurement. Each of these point here is a separate R2 measurement. So you get R2 effective at every value of CPMG. Okay, then you plot those R2 effective as a function of the new CPMG, and in the end you will get this plateau, and that is your true R2. And if you have a decay like this going, it indicates that you have the chemical exchange contribution happening here. Okay, and if you don't find a decay like this, it means okay. If you don't find a decay like this, it means there is no exchange contribution, then you are perfectly fine. So that means there is no exchange contribution. Therefore, you figure out this, whether there is exchange contribution or not. Okay, so here are some typical examples here for, and these are measured and these are fitted here these are at 2 different frequencies, 500 megahertz and 800 megahertz for different residues. Okay, so you see different residues behave differently. All right, but the same protein here, you are measuring this for different residues, because in the HSQC spectrum, because you are taking the HSQC spectrum, right? This is proton and N15. You have various peaks there. With every peak you are going to measure. So you measure the T2 values for every residue. So therefore you will get a sequence-wise information about the R2 values. Now you see here this alanine 6, okay, has a significant contribution. The decay is so much here. So there is a significant variation as you go from here to here. The new CPMG is varying from 0 to 1000. Okay, so that much you do series of experiments there, and here it is at a different field. Okay, 500 and 800. Okay, these are the numbers. Okay, so alanine 6 at 25 degrees. So this the decay is there. You go to aspartate 16, is much less. The decay is much less, is much flatter, and you go see here for aspartate 16 this is at 25 degrees, and you go to 45 degrees here, so the decay is much more. The exchange rate is more, so it will depend upon the temperature also, right? If there is exchange, certainly exchange will be influenced by the temperature. Therefore, you do temperature dependence also in this case. So therefore, you will see the temperature dependence aspartate 6 in the same way. This was not present at 25 degrees, exchange which was not contributing. You see there is a significant contribution at this. That means that it was present here also, but small, less. And if you increase the temperature, it has exchange contribution is increased, and you will start seeing such a great decay. And in this case, what is present? This is alanine 6 at 25 degrees and 45 degrees. There is no exchange, because you already gone over to the high temperature. I mean the fast exchange. In that case, of course, it will not affect your line weights. So, and you see a flat region here. Okay, so this is so these are the fold and unfolding exchange rates, ppm. Okay, these are two typical data sets which are there for given proteins. Now here it is more for more data sets for different kinds of. You can measure this on proton, you can measure this on carbon, proton, carbon, and for various kinds of residues. You can see here there is no contribution here, almost flat, very little, and then this shows much larger. N26, this is using proton for the H beta of N26. This is carbon here doing the C gamma. I cannot read that here. That is C gamma, isn't it?
C gamma, right.
So you can see for the asparagine 26, the carbon, if you see, you may not see in a particular nucleus, but you may see it in other nucleus. Because this exchange rate, if you remember, depends upon, or the exchange contribution depends upon three things. One is the populations, second is the exchange rate, third is the chemical shift difference between the two positions, omega A minus omega B. These are two sides, it will depend upon this difference. So that's why, depending upon the difference between these, relative to this, what is the exchange rate, whether that will contribute to the, we have seen that in the last class. When you go to intermediate exchange, means they are close to this value, exchange rate is close to this value, see quite substantial broadening. If you are at very low exchange rate compared to this difference, they are very sharp lines. If you go to much larger value or exchange rate compared to this, then of course you have a sharp line in the middle at the weighted average position. Again, exchange contribution is not there, but you will see only an average peak in that one. So therefore, the temperature affects in this manner, and the chemical shift difference between these, the two sides, will also influence. That's why, so when you see different nuclei, whether it be proton or nitrogen or carbon, this will show up. Within one nucleus it may not show up, but it will show up in another nucleus. So that's why it is necessary to figure out the residue-wise changes that are happening. We need to do it at various nuclei. You do proton, carbon, you can do proton, nitrogen, and so on and so forth. So all of this, so for so many residues, you can see different behaviors, and this relaxation dispersion experiments are extremely useful in this sense. Okay, now how do we estimate the exchange rates from here? So this is an equation here. So, or this, let's go through this equation a little bit. R2 is given by, what are the factors which I mentioned to you, already mentioned to you some of these things there. Between the two sides A and B, PA is the population of the A site, PB is the population of the B site, okay, and K exchange is the exchange rate, and new CPMG is what we actually put in your experiment there, okay, and so it will appear in this. K exchange is present here, and there is a tan hyperbolic. So this is the equation. We will not go to the derivation of this, but this is what is used there, okay. And then phi exchange, this term which is present, is proportional to PA into PB is equal to PA PB into delta omega AB square. And what is delta omega? Delta omega is the chemical shift difference between omega A and omega B. Omega A minus omega B is proportional to the square of that. Therefore, you see the measured R2 will depend upon the populations of the A and the B states, intrinsic exchange rates of the two states, the frequency difference between the two states, and the way you perform the experiment, new CPMG. What is the value of new CPMG you get? So this is the R2 observed or the R2 effective. Okay, so in the intermediate exchange rate, where Kex is equal to delta omega AB, the transverse relaxation is given by the Carver-Fisher expression power. Okay, now that's an approximation there. Okay, so these are the factors which are responsible for your measured R2. Okay, so that is one way of measuring the exchange rates in a system, in a protein chain. So you have to do a series of R2 measurements by varying the new CPMG, and you will get you will identify whether there is exchange in particular nucleus, particular residue or not. Okay. Now we go on to another method to determine whether there is exchange at a particular site or not. And this is called as the temperature dependence of the NH chemical shifts. See, typically if there is a NH...
Sir, there is a question.
Yeah. Where? Yeah.
Sir, where there is nothing.
The question?
PPT bunker.
Sir, where the exchange is affected by different spectrometer meshing.
It is. It is affected because omega A and omega B depend upon the spectrometer. Right? The ppm may be the same on a different spectrometer, but the omega A and omega B are dependent on the spectrometer frequency.
Yeah, delta omega is different.
Okay, so because delta omega AB, that is the difference between the two. Therefore, what is intermediate exchange at one spectrometer frequency may become fast exchange at another spectrometer frequency, or it can become slow exchange, intermediate exchange at some other frequency. Therefore, that's why it is necessary to measure at more than one frequency if you want to get the proper exchange rates and all the contributions with regard to that, to understand the phenomenon very well. Okay, so one has to be aware of that. So sometimes you may find that a particular frequency there is no exchange, but it does not mean that there is no exchange. It is just that your parameter, the spectrometer, is not able to detect it. Okay, so therefore, in order to detect that, you will have to go to some other field. That's why you see in those data sets which I showed you, they are measured at two frequencies, 500 and 800 megahertz. Okay, and somewhere it may have the same thing is true with the T1s. You also saw the T1s. So the T1s you see, it is dependent on the spectrometer frequency. That is because of the spectral density function and things like that, right? So in the same way, the exchange contribution will also depend upon the difference in the frequencies between the two, and therefore it will depend upon the spectrometer frequency.
Sure.
Is that clear? Okay.
Sir, I got it.
Okay. Okay. So no, this is another method of estimating if there is a exchange contribution there, chemical exchange going on. Typically, if you have the protein where there is you have the alpha helix or beta sheets or something like that, the NH proton is involved in a hydrogen bond. Either it is doing a hydrogen bond with water or it is with some other carbonyl inside your in the protein chain. Whether it is alpha helix or beta sheet, there is a hydrogen bond. Okay. Now, typically, the chemical shift will depend upon what is the strength of this hydrogen bond. So therefore, if the hydrogen bond weakens, the chemical shift will change. Okay. So therefore, and the chemical shift observed will move to lower field if the hydrogen bond, it will move to upper field if the hydrogen bond gets weaker. The hydrogen bond causes a downfield shift, right? So for example, you remember in the nucleic acids, the base pair hydrogens, iminoprotons are somewhere around 12 to 14 ppm. Okay, or even in the NH bonds, in the beta sheets, in the proteins, the chemical shifts are somewhere like 8 to 9 ppm. And then if there is a hydrogen bond is broken, the chemical shift will go up. So it will go to 7 ppm or things like that. There is a shift in the therefore, you see here, the observed chemical shift has a temperature dependence. Okay, that is a delta naught in the absence of any this one, the intrinsic chemical shift, plus G times T. G is the gradient in the temperature, and the T is the absolute temperature. So it will observed chemical shift will depend upon this intrinsic delta naught of the NH proton plus G times T. Okay, the gradient. So if you plot this delta omega with the T, then you will see actually a straight line with a negative slope by and large. That means the slope here is the G is a negative term, negative quantity. Okay, so therefore this is the kind of a thing which you will normally expect if there is with the temperature. You measure the chemical shift of the amide protons and increase the temperature, record it as a function of temperature, you will find that normally it should be a straight line like this. Increase in temperature weakens the hydrogen bond, and that's why the chemical shift will go up, upfield shifts. Okay, now what happens if there is a chemical exchange? Consider the situation like this. You have the state 1 and the state 2. This is the native state and the excited state. The population here is P1 and the population here is P2. There is an energy difference between the two. There is actually an energy barrier there. Okay. So, and the state 1 has a chemical shift dependence on temperature like this. And the state 2 has a temperature dependence like this. Okay. And now if there is an exchange happening between these two states, then the observed chemical shift will be a weighted average of these two chemical shifts. And the P1 and P2 are the populations, right? So therefore it is a weighted average. Therefore, you express this in the form of, after some simplification in the mathematics there, you will, and because P1 and P2 will depend upon the free energy difference between the two, right? Therefore, the free energy comes into the picture automatically. Free energy comes and the temperature also will come. The populations will depend upon the temperature, and therefore, the observed chemical shift will also depend upon the temperature and also depends upon the free energy difference between the two. So, delta observed will have this kind of a formula. Delta 10 plus G1T plus inside delta 20 plus G22 into the e to the minus delta G by RT divided by 1 plus e to the minus delta G by RT. And those are for physical chemistry based, you can try and derive this equation. Okay. And delta G is the free energy difference between states 1 and 2. And G1 and G2 are the gradients of linear temperature dependence of chemical shifts of states 1 and 2. And this need not be the same. It can be different for different residues or different for different states. When I say the same residue, okay, is in two different states, we're talking about the particular NH proton of a particular residue in two different states, excited state and the native state, and the gradient of the gradient dependence may not be the same. Therefore, the G1 and G2 may not be the same. We have to keep that in mind. So therefore, these are independent variables, G1, G2, and delta 1, 0 and delta 2, 0. So therefore, your observed chemical shift will look like this. It is not a linear thing anymore, as we show in the previous one, and this is called as the curved temperature dependence. So if you plot the chemical shift as a function of temperature, you may find curves like this, curves like this, curves like this, or sometimes even like this, going up also. See, like, so what you do, how do you figure this out? What do you do there? Okay, now what you do is you fit this to each of these, you fit this to a linear equation as if it were a linear state. Then you will find that it does not fit. So therefore, there will be curvature that is called as the residual after linear fit. The residual after linear fit will have a curvature. Okay, and you plot this as a function of temperature here. You can have the curvature which can go like this, convex, or it can go down also. So the concave. So you can have concave shape, the residual after linear fitting can have a concave shape or a convex shape. And when does that happen? This will depend upon the relative magnitudes of delta 1, 0 and delta 2, 0. Which one is upfield, which one is downfield compared for the two states. So if delta 1, 0 is greater than delta 2, 0, it means that delta 1, 0 is more downfield compared to the state 2. And otherwise if this is upfield compared to this, you will have a concave shape like this. So therefore, you can have curvature will be seen for delta G less than 3 kilocalories per mole. You may not see it very, if the thing is larger than 3 kilocalories per mole, then you may not be able to see because the exchange rates are very slow then. So you may not be able to see the differences in that one. Okay, the effect of chemical shift differences, and the C is the effect gradient differences here. So here, these are the different, this is the calculations for particular things, typical shapes, and these are actual simulations. Effect of chemical shift, certain chemical shifts have been assumed and shown, okay, this is the way it is coming. And if for the same chemical shift, if you change the gradients, G1 and G2, okay, here you change the delta 1 and delta 2 in this case, and if it is the gradients, the G1 and G2, how does it affect this residual chemical shifts? So these are called the curved temperature dependence, and this is the curvature. The extent of curvature is reflecting upon the exchange contribution. How much is the exchange between these two states, or the populations of the two states? Okay, so, and you see here, in a particular protein here, HSKP1, and this is actually again, well, now this is not in press anymore, it is already published. This is from one of the students' work in IIT Bombay. You see fantastic curved temperature dependence. So much chemical exchange, E150, A151, Q152, K155, all of these are concave differences. And you also have convex here. Convex, and there is a mixture here. More complicated situation here. It can also happen that you will see a flat one. Sometimes it can happen that. And that will when the delta G is higher, or the chemical shift difference between the two is smaller. In that situation, you may not see this one. So therefore, one has to do this at multiple frequencies to figure out what are the chemical shift, what are the exchange contributions there. And this is even a complete data set of that one only, that is all the residues. You look at how many residues are showing. Okay, in this, for example, it is not very large. It's not very large here. These ones, they're not very large. But you have all kinds of things, concave, convex, temperature dependencies here. This is a beautiful method of analyzing, and this is faster also. You do one experiment. Unlike in the relaxation dispersion experiment, you have to do so many R2 measurements. You have to make several R2 measurements by varying the UCPMG. Okay, and then it will tell you whether it is exchange contribution or not. But here you do one experiment. You take the protein, measure the chemical shifts as a function of temperature, and that's it. So amide proton chemical shifts to do. So this will be a much faster way of recording the data and identifying the exchange contributions in different residues. Okay, so this is the summary of all of that, what is there. So this is the protein, which is, okay, once again, this is, I did not update this. So this is the data is already published. So in these areas, so this protein has this sort of a structure, okay? And here it is a beta sheet here, the beta sheet, small stretch, and you have a helix, the helix, and there is a helix here, and the long loop here. There is a helix here, a long helix. See, this helix continues from here. It's a very long helix. The loop here, here, and here. Okay. Now these dots here indicate the curve temperature dependence in various places. See, by and large, you see these are seen mostly in the loop areas and sometimes in the helical areas also. The unstable helices, if they are there, then you will see them also. And you will see both concave and convex. The black dots indicate convex profiles and the red dots indicate concave profiles. So no matter whether it's concave or convex, it indicates that there is a conformational exchange and the protein is accessing other conformational states in the ensemble. Okay, so therefore this is the kind of this is indicated here. All the red things are the ones where the molecule is undergoing exchange control, is seeing exhibiting exchanges, and many of them are in the loop areas. Some of them there's a few things in the helices also. For example, this is inside the helix, and these ones are, this is the end of the helix, this is the middle of the helix, and you see here some helix is there. So which means these helices are not very stable. There can be some breaks in between there, probably because of some whatever the reasons are, and many of these places you see also have certain residues which are showing. In the loop areas also you have this. So by and large you do have, but the extent of this variation will vary from the structured regions to the unstructured regions.
Sir, that means if you are increasing the temperature, in case of convex means your hydrogen bonding strength is increasing. The chemical.
That's the case. See, that is delta 1 less than delta 0, delta 1 less than delta 2, or delta 1 greater than delta 2. Initial, delta 1 0 and delta 2 0. That determines what is the, whether it is concave or convex. It will determine that. And accordingly, we can see that the chemical shift will change in that manner. So the residual, if it is concave, then it is coming down. So therefore, it is
initially negative, then it is positive.
That's becoming positive. Yeah.
In other case, it will be initially positive
and then
negative. So
that's right. So it is not linear. It's not linear, and it will
But how, as you said, that the temperature changes the hydrogen bonding strength, na?
Yeah.
So that means there are some other parameters are also there. It is not that.
Yeah. That is hydrogen bond. If it is just exchanging with water,
yes,
that is the linear dependence. Hydrogen bond is getting weakened.
Yes.
But here it is not exchanging with water. It is accessing a different conformation. So the effect
due to that, the hydrogen bonding strength is changing.
Yes, exactly.
Okay, sir.
Okay. Okay. Now this is in another protein. This is the sumo. Sumo is that was the HSKP1, and in this protein also again you can see these for various residues, and in this one there is very little difference. Here there is a large. This residue is very large, and this is what is done here. This is as a result of urea unfolding. What is the consequence of unfolding the protein? Okay, so you have the 0 molar urea, protein is well folded, and you are trying to unfold the protein because you're trying to study, suppose let us say trying to study protein folding. Which are the areas which are very vulnerable, where it is likely to fold fast or where it is likely to unfold fast, whichever we want to look at it. In 0 molar area, the protein is fully folded. Okay, now if you measure this temperature dependence here, you see the Q53 has substantial curvature. And these other residues don't have so much, except this 57 has something which is close. 40, for 35 is almost nothing. 46 is a little bit of this curvature, and 60 has almost nothing. Now you denature it by adding, let's say, 0.35 molar urea. What does the urea do? Urea goes and interacts with the carbonyl groups in the site in the backbone and tries to unfold the protein. And this remains thing like that. Still, the Q53 still shows the concave dependence. But now you see K46, its convex nature has increased. So it is unfolded. It is unfolded. It is now accessing more conformations, additional conformations, and the propensity of that is higher now. And the 35 is still not changed. It is not unfolded there. That is not exchanging. Therefore, you follow the pathway of unfolding by this process, by looking at the temperature dependence of the NH proton chemical shifts, by looking at the curvatures of this amide proton chemical shifts. So this is not affected, interestingly, and you see Q53 is close to Q57, but you still don't see this such a big change. Why is that? That's probably because the chemical shift difference between the two states here, it is not very large. Okay, and that's why you are not able to see this difference here. And the same thing is true with 60. Same happens here. If you go to 0.7 molar, still nothing is seen in these places, but this now acquires a large convex dependence. This further increases, this remains the same, and you can see how the changes happen as you start unfolding the protein. Still, it is still not, of course, very large unfolding. It is still a very, in the native state ensemble only. Typically, if you plot the fraction unfold and you plot the urea concentration here, typically the curve will be like this. Unfolding curve will be like this. The fraction unfolded. This is fraction unfolded. And this is still in the native ensemble. Okay. It is not yet started unfolding. It is the native one, but it started becoming weaker. The interactions are becoming weaker. And that reflects in the conformational exchange, or the accessibility of the excited states. So you can see that even in this area, typically this midpoint occurs somewhere around 4 molar or something. And we are talking about 0.9 molar, you are somewhere here still. Okay, so therefore, even in that stage, you can see how the protein is getting destabilized. As a result of destabilization, the more residues are accessing excited states, the conformationally excited states, and it is you can see that in the temperature dependence. And these are very simple experiments to do. Doesn't require too much. You do series of HSQCs as a function of urea concentration in this case, or in the previous case. Of course, these are temperature dependence. The temperature dependence is at different urea concentrations. Okay, now this is the summary of all of that, which is indicated here. The native protein, 0.35 molar urea, 0.7 molar urea, and 0.9 molar urea across the length of the chain. And what we see here the structure of the protein is indicated here, the secondary structures. And this is the beta sheet. Beta sheet is the long beta sheet here, the long beta sheet here. There is a helix here, sheet, helix, and sheet. And you do see some of these things at the sheets. Okay, very little at the some of the, and in this loop, of course, this is a completely flexible one. There is no structure there. There is no structure in this N terminal. From 1 to 20 residues, there is a completely flexible chain. So therefore, it's rapidly fluctuating, and it is always accessible to the water. There is no question of exchanging between two conformational states there. So it's very rapidly exchanging. Therefore, you don't see any such effects in that part of the protein. Where there is a reasonably good structure, and the exchanges and the conformational flexibility is not very large, there you will start seeing such kind of effects. And you see here in this loop area, you do see some exchanges, and you see that increases as you increase the urea concentration there. And in the sheet, again, you see quite substantial changes as it opens up. This opens up. And the loop area, of course, this is opening up. And this helix also starts opening up here. You see exchange contributions. And you see this also, you see exchange contributions. I forgot what is the square versus this may be the concave or convex changes. That could be.
Yeah.
Yeah. And then you have this in the loop areas, you have several of those. And in the beta sheet at the end points here, and in this also in the beta sheet end points, in this helix also you see this opens up very late. So only at 0.9 molar, in between you do not see it. Okay, so here also you see here, and then native state a little bit here you see also at 0.9 molar urea. This also opens up pretty late. This is a small contribution there, and this is substantially opened up there, and here it opens up only at 0.9 molar urea. Here it is always, this is the end of thing. So therefore, these parameters which are there, as I said, they depend upon the factors of populations of the open and the closed states and the chemical shift differences between the two. So if you don't see at a particular site, it does not necessarily mean that there is no exchange happening, but one has to do it at multiple spectrometer frequencies for those. Okay, all right. So that is with regard to the how you can use temperature dependence for measuring the conformational exchange. And now we go into the another technique which is called as hydrogen deuterium exchange. And those ones, what we saw in the temperature dependence on those ones, they access a particular time scale of motions. Okay, time scales of excited state exchange between the native and the excited states. Okay, so typically that is in the microsecond time scales, and you go to microsecond to somewhat milliseconds. Now we go to hydrogen exchange, you sample the different time scale of operation. Here it goes from seconds to milliseconds to seconds. Okay, that time scale of operation will go. So therefore that dynamics you measure from the hydrogen exchange. So therefore you see we considered different techniques. Relaxation dispersion, which is R2 based. R2 based is sensitive to the nanosecond time scale motions, and temperature dependence is we saw, and that is sensitive to the microsecond to nanosecond, sub-nanosecond time scales. And now we are approaching the millisecond to second time scale motions. Okay, and how does this work here? Now let us consider this a particular protein. This protein, it has a helix here, red is a helix, and the cyan is the sheets. And all these individual residues are indicated by spheres, small spheres. And this is now in water. What you do, you lyophilize it and put it in D2O. Initially, all these are protonated. They are all protons. Now you put it in D2O. What happens when you put in D2O? As a function of time, you monitor it. The protons which are on the surface of the protein, they will exchange. So they will become red. See, all those which are here blue, they will now become red. Which are on the surface of the protein, they are red. Which are in the interior of the helix, they don't exchange. So they remain as blue. You continue this dynamic and exposed, amine hydrogens exchange rapidly. And if you continue this for longer time in the same manner, more and more residues will get exchanged, and this is the protection. This tells you how much deep inside a particular residue is in the protein structure. So the ones which are on the surface, they will exchange faster, and ones which are in the interior, they will exchange slowly. Therefore, you need to give more time for the D2O to penetrate into the structure of the protein, and exchange will happen into the interior things. For example, you see here all the things within the helix have also become red after a long time. So protein sample is exchanged into D2O and disappearance of NH peaks in a 2D. So when this happens, what is the consequence of that? If it gets exchanged in D2O, proton becomes a deuterium. Then if you record an HSQC spectrum, you will not see those peaks. Whichever ones are exchanged, you will not see those peaks. And these are the HSQC spectra at different time points. Okay, or the HMQC. You can record HMQC or HSQC. So here you see, here all the protons are seen. Okay, all the residues are seen. Okay, some of them are labeled here, things like that. Now you wait for 9 minutes. You give here a time 9 minutes. So many peaks have disappeared because these ones have exchanged with D2O. So they become deuterium instead of proton. They become deuterium. You will not see those. Go to 63 minutes. More have gone. Okay, and you go to 133 minutes, these are. So look at what is the time scale here. You are going from seconds to minutes. So the protein is pretty stable. So it takes a long time for the protons in the interior to exchange. Now, in order to do that, there are various kinds of mechanisms which have been proposed. The protein has to unfold and exchange, unfold again, and things, the dynamic equilibrium which is present in the folding, unfolding equilibria. And that causes the protein to exchange with the D2O. Okay, so this is a method to figure out what is the time scale of this protein unfolding or the folding, and exchange rates of the deuterium of the protons. So if you plot this, the observed NH intensity loss can be fit to a simple exponential to measure an exchange rate. Okay, so it is a slow function of time, right? So the recording spectra in this one, see, it is not only peaks disappear, but some of the intensities will reduce also. So you can monitor as a function of time. You have to record spectra at several time intervals quickly in quick succession so that you can actually plot a decay of the intensity of the individual peaks as a function of time. Okay, and that is what is shown here. So if you plot this as a function of time, so several different ones decay. So you see so many, these are all different individual HSQC experiments. Okay, you have done several HSQC experiments. You can do an HSQC experiment on an N15 labeled protein. You don't need a C13 labeling here. You just want an N15 labeled protein, and you can record the spectra at different time points. Or if your peaks are well resolved, you can also do that in your 1D spectra, amide proton spectra. You can measure the amide proton intensities. So that is also possible. So, but if proton is crowded, then of course you need to do HSQC spectra. Then you have to record HSQC spectra quite rapidly to be able to monitor these changes as a function of time. Now you see there are three particular residues have been taken here: valine 17, isoleucine 11, and asparagine 73 in a particular protein. It doesn't matter. So the exchange rates may vary from minutes to months, and in BPTI actually it even goes to years. Some residues which are in the interior of the BPTI structure do not exchange at all. They are so stable, and these ones have very different exchange rates. You can fit this to an exponential. Sometimes you can fit to a single exponential, but sometimes you need to fit to a different exponential, two exponential. That means there are more than one mechanisms which are operating. If it has to be fit to a multiple exponential, that means there are more than one mechanisms which are operating, and they are having different time constants or the exchange rates. So, and then you will have to fit those things to this kind of equations. This is a single exponential fit, and this is the two exponential fits you will have to do, and you can figure out what are the different contributions there. So therefore, this is telling you about the hydrogen deuterium exchange. Majority of the NHs that exhibit slow exchange rates are located in secondary structures. Fast exchanging NHs are located in loops, N and C terminal regions. And that is, you see here, this is the helix 1, turn, and in these areas you have things which are exchanging very rapidly. There are a few in the turn also. Okay. So this is how you measure the exchange rates. Exchange rates are very low in the areas where the protein is stable. The helix here, they're stable, and the loop areas and things like that you will see. So this allows you to figure out the contribution or the process of unfolding of the protein. That is also dynamics in the protein, right? Protein unfolding is also dynamics. Protein folding, unfolding is a dynamics. Okay, how do we understand this? We understand this in the following manner. You have this exchange happening here. This is the D2O, of course you get the AD here. This is the chemical reaction which is happening. Now here is the protein. The protein opens up with the exchange with the rate constant K open, and exchange closes with the rate constant KCl. So if this is the folded things like that, it opens up into this manner, and once it is here, then it is a exchange. It goes up. This is not reversible. Once it goes, it does not come here. With the deuterium it exchanges, you get the deuterium here. This is the local unfolding mechanism. This is the local unfolding here, happens only in this area. There is another thing which is called the global unfolding mechanism. The protein actually unfolds completely to this, and then the exchange happens, KCH, to get a deuterium here. So what is the mechanism? Of course, this, one will see it as a result of when you measure it on various residues, you will figure that out. So what happens there is here, the K observed will be dependent on, will be given by this equation, K open into KCH divided by KCl plus KCH plus KC open, and this is approximated to K open into KCH divided by KCl plus KCH, and this exchange rate is this exchange rate is much smaller compared to this sum. Therefore, this term is neglected here. Now, there are two mechanisms which are indicated here. One is when the closing rate is much smaller than this rate. That is this rate. This closing rate is much smaller than this rate. That means once it goes, it's very unlikely it will come back and it will immediately go over there. The protein chain will unfold and go over there. This is called as the EX1 mechanism. EX2 mechanism is when the closing rate is much larger than K chain. Therefore, there is much higher probability of the protein coming back here rather than going here. Okay, so therefore this one is much faster than this. Okay, that is called as the EX2 mechanism. So in this situation, you can make approximations here. Depending upon which one is much larger than the other, you can neglect certain terms, and you will find in this situation the K observed is proportional to K open divided by K close into K exchange. Okay, this is the change. What is this here? K open upon K close. This is the equilibrium constant. Equilibrium constant of the protein folding and unfolding here. The local equilibrium constant there for this. Okay, unfolding folding equilibrium and unfolding equilibrium constant multiplied by this exchange rate. This we can measure on an independent one. This doesn't change too much. This is for an unfolded protein chain, whatever is the value, you can get these ones. But this is a very useful information you are getting. Under the EX2 mechanism, you are able to get the equilibrium constant of this. The equilibrium constant is related to the free energy. Right? Therefore, you get the free energy of the protein unfolding mechanism. So now you can measure this unfolding at different residues. Under the EX2 conditions, the measurement of exchange rate allows determination of equilibrium constant between closed and open states, and thus the free energy difference. Okay. Now, for exchange enabling, if local unfolding is the rate limiting step, okay, and that is different residues will yield different free energy values. That is, this is the rate limiting step. Okay, local unfolding. If that is the rate limiting step, then different residues will give you different values, because at different points it will be different. If global unfolding is the rate limiting step, all residues would yield the same free energy value. That is, if you have this mechanism which is going down here, then you will see the same exchange rate for all of them. Therefore, you can figure out what is the mechanism of unfolding. How does the protein unfold? Does it go via the local unfolding mechanism, or did it go by the global unfolding mechanism for the protein to exchange? Therefore, hydrogen deuterium exchange provides an extremely useful tool to measure the one thing, exchange rates, find the local stabilities of the individual residues, and also the folding mechanism, folding unfolding mechanism. How does the protein unfold? How does the protein fold? Okay, now we move on to another method of estimating the exchange current. Okay, now maybe we'll take a break here. We'll take a break here.
So the break for so when we are exchanging with deuterium,
Yeah.
the protein conformation will have slight change or
not much. The hydrogen deuterium sizes are not very different, although their properties are somewhat different. Is not very different.
Nuclear property will change, but
nuclear properties are different, but the hydrogen bonding possibility potentials, they are all
slightly changed.
Slightly changed. There will be small changes in the chemical shifts.
it's very small.
Yeah.
And see, when you are recording, also the exchange is going on.
Yeah.
So
that's why I have to do it faster. When you want to do that,
so when you are doing this hetero HSQC, how much time
Okay. Now, this is another method of studying exchanges. In fact, this idea has been borrowed from the imaging people. This is called chemical exchange saturation transfer, or CEST. What is the idea here? Just look at this. Here is a small solute. This is a small molecule. This is a solute, and this is water here. This solute has an exchangeable proton, NH. Okay, this NH exchanges with water. Okay, now let us say this hydrogen has come here. Okay, another one that has come here, is here and here and so on. So few of them. It is so few molecules have gone there. But so therefore, if you and of course the reverse process also will be happening. It's going back and forth. This also will be happening. Now, once you saturate it, if you have two signals there, let us say you have one signal here and another signal there. If you have, that is indicated here, okay, anyway. So, if you saturate it one place, and if this is exchanging with this position, this saturation will get transferred to this, and the intensity of this will go down. Saturation meaning what? The intensity goes down, right? If the saturation is transferred to this signal, the intensity of this signal will also go down. That is called a saturation transfer. Okay. Therefore, if I irradiate this amide proton, this NH here, and this gets transferred to this, then it is essentially saturation transfer is happening to the water signal. Therefore, the water signal will go down. So then we might say, then depending upon how many protons are there, only that many water molecules will get changed. So what is the big deal? Because this is anyway very small amount, and this will be in molar quantities, so therefore the big small change. However, there is a trick here. Trick is that before this fellow relaxes, if this reverse process is faster, okay, the saturation, this proton is already gone there, saturated proton is already gone there, but the one which is unsaturated, this proton will come here. This proton will come here. Now it is ready to get saturated again. So now this will go here and another one will come there. This will get go there and another one will come there. If we continuously keep on pumping energy into the water signal, therefore although this concentration is very small, you can saturate a large amount of water protons. You see, that is the trick which is used. It's called as chemical. Therefore, saturation transfer is used to enhance the transfer of information, and you will get the signal like that. So this is the, for example, you have the proton signal here and the water signal here. Now you are irradiating this over a period of time. Slowly over a period of time, you continuously irradiate it. Then you will see in the beginning, the signal is here, the water signal is here, and you continuously saturate it, then this proton saturate signal will go down. Okay, so therefore this is the technique which is used in the imaging experiments. Now what you can do is, this is the useful hold you have. You can keep changing this. You can keep changing this, and then it will tell you which are the ones which are exchanging. That is an extremely useful entity. And that is what is used in this thing here. In CPMG based relaxation dispersion experiment, we already saw that allows you to detect this exchange contribution in the particular protein, okay, with the different residues. Now, it will tell you, even if you are not able to see a small signal, you are able to see with what it exchanges. Here you are not able to see what it exchanges, right? You are only seeing the particular residue exchanges within another state B, but we don't know what that B state, because you don't see that signal. But here in this CST signal, you have this other small signal which you may or may not see. Signal may or may not see. The signal is there. It's a broad signal, and that is, for example, here. This is, and you keep on varying this position here. Okay, then somewhere it will hit. That means that particular residue is interacting with this, exchanging with here. And that is an extremely powerful tool to identify the exchanging state. Okay, what is the chemical shift of the exchanging state? You can figure that out. So if you have a protein chain, let us say the protein which has hydrogen exchange, and it undergoes a conformational exchange to some other state here. And this is in a small, okay, that is in the next slide probably already. Studying invisible state. These are called studying invisible states by CAST. Yeah, for example, here it is already there here. Now, here is an HSQC spectrum. Okay. Now what you do is there is an exchange here between G and D. This is the excited state is 1.5% and the native state, ground state is 98.5%. There's an exchange rate here happening. This is so small that you don't see the signal here at all by and large. Okay, it's extremely small. Now therefore what you do is you keep irradiating this along this axis. Even though you don't see the signal there, you keep putting the RF. This is a weak B1 field is put there. You put a B1 field to saturate this, put this field at various places. Okay, that is, if this is the N15 axis, keep changing your field along this axis. See, you see these experiments at where you do this experiment by putting the B1 field at various points. Okay, but when you are putting the thing at this point, you suddenly start seeing the effect. That means this chemical shift is exchanging with this. Okay, although you don't see the signal here, you may not, in the absence of this, you may not see the signal. But when you saturate it like this, you start seeing an enhancement which will tell you that, okay, here is a chemical shift which is actually exchanging with this ground state. This is a very powerful tool. The things which are invisible in the normal situation, you are able to see, detect them here. Invisible states you are able to detect by this process. Although you will have to do trial and error, different experiments, you have to keep varying this at small intervals. Keep changing this B1 frequency, but all small RF field you have to apply, and then you will see the effects of this going. And suddenly you will find that, okay, at some point you see, at other points you will not see it, because there is no signal there in those ones which are exchanging with the water or some other state, not necessarily water. The idea is taken from the imaging. In the imaging case, it is the water. Here it is the ground state and the excited state of the particular residue. Okay, so which residue is exchanging with what excited state? That is what we are trying to figure out here. So therefore, if you identify that this particular residue is getting affected, that is this one state here, then you will know what is this exchanging with and what is the chemical shift of that exchanging state. You can figure that out. So you do that with all of these, and that is what is shown here. So you measure this, then you can measure the R2s of these ones, and you have the exchange rate measured in various places. You identify for each of these residue the excited states, and then you can measure the R2s of those ones, because this exchange process is reflected in the R2 values. So you can measure the R2s of those ones, and this is an extremely powerful tool to identify the excited state and measure the properties of the excited state, even though those are not directly visible in your HSQC spectra. Okay, I think we'll.
So yeah. For each of these residues, there can be several
conformational states.
Achha, so
if it is exchanging
in case of, let us say, around residue number 39 or so, now you can see 1, 2, 3.
No, these are at different places. These are not the same. This one. These are at different places. They are not the same residues.
They are around 40.
They are not on the same line.
Around 40, there are 3. I could see.
May not be the same line.
No, they are not in the same line.
Okay.
40, 41.
They are different.
There is a possibility that
it can have. It may be exchanging with more than one slow exchange. Then it is possible to see those different.
As you are changing, you will be able to see that one.
Exactly. Exactly. This is a very powerful tool, extremely powerful tool, even though you don't see the signal.
Yeah. If it is 1%, you will not be able to see
you will not be able to see it, yes, exactly.
But if you keep it for some time, you see the signal, it decreases.
That's right. And of course, you can change this power also. The B1 field irradiation power also you can change. Therefore, you do the experiment at more than one power levels.
So you can increase initially and then you can fine tune and exactly.
Yeah. Okay, so this finished, you put the next one. Okay, fine. So now we move on. So we have seen how to measure the dynamics in the proteins. Now we move on to the next topic, which is the protein folding. And protein folding, there is a particular famous paradox called as Leventhal's paradox. And as Leventhal noted that because of the very large number of degrees of freedom in an unfolded polypeptide chain, the molecule has an astronomical number of possible conformations. Why? Because every peptide, dipeptide, there is a 5 side torsion angles, right? 2 torsion angles, which are the degrees of freedom for every amino acid residue. So if I have 100 amino acid residues, then there will be 2 to the power 100 degrees of freedom, and therefore he made an estimate. The molecule has an astronomical number of, an estimate of 10 to the power 300 was made in one of his papers. Okay, for example, a polypeptide of 100 residues will have 99 peptide bonds and therefore 198 different 5 side bond angles. Each of these bond angles can be in one of the 3 stable conformations. Actually, there is this is not bond angle, this is torsion angle. I think this is the mistake there. It's not a bond angle, this is the torsion angle. Phi and psi are torsion angles. Okay, so it can be in one of the 3 stable conformations, which are the Gauss and trans conformations. So the protein may misfold into a maximum of 3 to the 190 different conformations. The point is that, and it is an enormously large number of degrees of freedom. You want to sample all of those, it can take years, and it's sometimes this is age of the universe. The large, longer than the age of the universe to arrive at its correct native state. Therefore, obviously, this is not what is happening. So therefore, the many proteins will actually fold in sometimes in minutes, sometimes in hours, sometimes even in seconds. So therefore, how does that happen? That was the basic question. Now, how do we use NMR to this? So protein folding is generally described in this picture. So you have the so this is the way the fold. I should have put this. It's not a readable thing. It's ulta ho gaya na. Should have put it like this.
Transitions.
This is the folding transition. So you have, this is the unfolded state. The top is the unfolded state, and the bottom is the folded state or the native state. This unfolded state is of higher energy, and there is no structure there. Therefore, it is very flexible. Literally, every residue accesses a larger number of conformations. Okay, and the native state is a is a very rigid structure, and it doesn't have too much of flexibility over there. Every protein, every residue is in a particular combination of phi and psi. Whereas here, all combinations of phi and psi are possible. Therefore, it is a very disordered state, very flexible state. Many millions of conformations are possible here, whereas there is only one conformation which is present here. So therefore, the protein has to fold, it will come down, and often one is describing this in this kind of a funnel diagram. It will, different pathways exist for different locations. There may be some barriers here. Different residues may fold with the different pathways. So it can happen in this manner. There are various energy barriers there. Sometimes it can get stuck in some of the intermediate wells. Then it may not be able to come out of that. Then it represents a misfolded state. Then it can lead to all kinds of diseases and things like that. Therefore, protein folding is a very important topic in structural biology, and also for with regard to the diseases. There are a whole lot of diseases which are related to the protein misfolding. Okay, now how do we study this? So here we have the protein chain, unfolded state, and this is the folded state, the same unfolded chain. As the protein starts to fold, what will happen? The chemical shifts will change. Okay, chemical shifts will change, and the motions also will slow down. Why will the motion slow down? Because the contacts are made. When the contacts are made, it does not allow the protein to be flexible, therefore the motions will slow down. And when the protein folds, then of course the environment changes, and therefore the chemical shifts will change. Then that means when the chemical shifts, you can calculate the so-called secondary shifts. The secondary shifts are the shift between the state and the completely random state. Completely random coil. If the chain residue were in the completely random coil state, what will be its chemical shift? And what you will measure is the observed shift. Observed shift minus that is shown in the next slide here. Now, okay. I have shown that in one of the previous lectures probably. But okay. So you measure the chemical shift delta observed between the folded and the random coil chemical shift. And that is called as the secondary shift. And I will illustrate this, how to study this, we using this particular example, sumo. Okay, this is the protein which has sheets and helices, and the lots of loops are there. Okay, now what you do is, you want to go from here to here. So you completely denature the protein first in 8 molar urea, and slowly start decreasing the urea concentration so that you start reaching here. Say 8 molar, 7 molar, 6 molar, 5 molar, 4 molar, 3 molar, 2 molar, 1 molar, 0 molar. This is the way you are trying to fold. That means you are trying to go from here to here. As you are decreasing the urea concentration, you go from here to here. And it will be reflected in the spectra. Chemical shifts will change, the line widths will change, as I said, because of the secondary shifts, and also the motions will slow down, and that will reflect in the nature of the chemical shifts. For example, if you see here, in this, what is the chemical shift range you have here? This is from 8.0 to 8.6 in all of these ones. I have here the range 7.0 to 10 ppm. In the bottom ones, this 7.0 to 10 ppm, and in these top 6 ones, I have 8.2 to 8.6. This is 8.0 to 8. So much narrower chemical shift range in the top spectra, and as it folds, then you have a much wider chemical shift range. Okay. Now these are the important. Okay, now I have here. Secondary chemical shifts are defined in this manner. Delta S is the secondary shift, delta observed minus delta RC. Delta RC means random coil. So if the protein were not folded, in the completely unfolded state, what is its chemical? That is called as a random coil. Therefore, this is an indicator of the degree of folding, how much the protein has folded. And this you can measure for the various nuclei. Okay, so you can measure this for the C alpha, the H alpha, and the carbonyl, all of these, and they have different patterns. So if you are looking at a protein, a residue which is in the alpha helix, which has the propensity to go into the alpha helix, then the C alpha secondary shift will be positive, H alpha will be negative, carbonyl will be positive. It is exactly the opposite if the structure is in the beta sheet. If it is the beta sheet, C alpha will be negative, H alpha will be positive, CO will be negative. So very good marker, very good indicator as to how the protein is going into what kind of a structure. Okay, now this is what is shown here with regard to the H alpha. You take the H alpha residue, 8 molar, 7 molar, 6 molar, 5, 4, 3 molar urea, and you see here much of this is in the positive state here. All this is the secondary structure here. This is that means this is all extended in the open state. Open state and beta state are nearly the same because this is the open state. Extended state beta chain is also an extended conformation. Okay, so here it is all beta. Okay, 8 molar urea. Now you start reducing it here. These numbers start going down slowly, differently at different places. Okay, all of them are going down differently at different places. You come to 6 molar urea, there is a sign change. Therefore, you found a small helix here. H alpha has become negative. H alpha negative. See here, helix. So therefore, you see a small helix here. And you go down to 5 molar urea, another helix here, this is the same, and this helix here. So stepwise, which portion of the protein is folding into what structure? You go to 4 molar urea, this helix extends further, and then this remains, but this fellow disappears. This is gone. It is there a little bit, but it is much reduced. You go to 3 molar urea, everything has gone. All of these helices have gone. What is the meaning? This is the great implication. What is the meaning of this? Okay. Now see the way the pathway it is indicated. This is indicating the pathway of the folding. How the protein is folding. Okay. Let's look at this further. In the same manner, you also look at the R2 values. How the R2 values are changing. As you go from stepwise, the R2 values, the sign change 8 molar to 7 molar, 7 molar to 5 molar, 5 molar to 4 molar. The way it is changing, this is also either positive here, the negative here. Different portions of the protein are folding in different ways, going different paths. That's why the R2 values are also changing. There is a slowing down at some point and not slowing down at some other points. Okay. So 8 molar to 7 molar urea, if it is positive, what does that mean? The R2 here is less than the R2 here. Okay. And same on this area, the R2 here, the 7 molar urea has a higher R2 value than this. Okay. So these are the indicators of the protein folding phenomena which is happening, and that is okay. It is schematically indicated in this area. So slowing down of the motions results in increase out exchange contributions will be contributing, though the R2s will go up. So you will see here the change in the color of the pink is indicating the R2 changes, slowing down of the motions, and the helix formations are indicated as was indicated there. Okay, so therefore 6 molar 1 helix, 6 molar you had 3 helices, and the R2 changes are happening in much wider range as you are going through the change. And 4 molar, this fellow has disappeared, this helix has disappeared. Okay, but the R2 contribution is happening there, slowing down is happening at more places, and these 2 helices are there. And come to 3 molar urea, everything has gone, all the secondary structure has gone, but the R2 values have increased all over most of the places. And many, you see substantial change in the coloring of this is indicative of that. And you go further down, of course, now this structure is getting formed here, and then finally it has to form here. Now, what is the implication of this? You look at this structure, this if I plot these changes that are happening in the R2 values by the color code of the individual amino acid residues, and mark these residues here in the red color. So what this means is that the protein is actually going, folding and unfolding, folding and unfolding, the exchange contribution is happening. Okay, therefore R2s are increasing. And so when the fast motions slow down, the slow motions will increase. Okay, intermediate exchange, that will the folding transitions will happen, means that is a millisecond to microsecond time scale motions will be there. Nanosecond time scale motions will go down. Okay, and that means this is the folded protein structure. In other words, this protein is now all set to fold into this state. What does that mean here? Then why these ones are disappearing? This is the implication that the folding does not necessarily follow the native structures, does not monotonously change the structure to reach the folded state. So in other words, these ones are kinetically driven. Whatever was the local possibility there, stability situation, it has gone there, but these are non-native contacts. These contacts which are made, helices which are made are non-native, they are not native-like. If the protein has to go over to the folded native state, then the non-native contacts will have to be removed. And that's why these ones are gone. It has come to a stage, now it is set to go into the proper native state. So the pathway of the protein folding is indicated in a very elegant manner here. It shows you that protein folding does not necessarily go through native contacts only. It can go through non-native contacts which are kinetically driven, and then they will have, if there are non-native contacts made, then it has to be removed, and then the protein will fold. Whether it can be removed or not depends upon the barrier there, and that is what happens. If suppose it gets stuck here, then it will not be able to come out of that. Then it needs to be completely misfolded. That protein will not fold. That misfolded state when will happen, it will lead to all various kinds of diseases. Okay, now we can use the coupling constants also. This is an HSQC spectrum, by the way, has an H alpha coupling constant here. HNH alpha coupling constant is there. Is in every peak you have this coupling constant. We can measure these coupling constants, which will also tell you about the phi torsion angle. H alpha, NH proton and H alpha coupling constant. In the gonadin denatured state, 6 molar, all they are very beautiful doublets. And they are all of similar coupling constants. Okay, now as you start folding, the coupling constants also will change. As approaches a particular structure, the helical structure or the beta structure, the coupling constants will change. Then you start merging here. Some will become further apart, some will start merging here. Then you can see changes that are happening in the coupling constants. This is HNH alpha coupling. Okay, what was that here? These ones have sort of disappeared there. Very weak ones. They have become very weak. They broadened out. Now this is another protein, HIV protease. Here I have given the summary in the initial state, what is all folding propensities in HIV protease on the basis of the secondary structures and the R2 values. R2 values are different in different portions of the protein. Change in the R2 value as you are going from high denatured state to low denatured state. That means from 6 molar guanidinium hydrochloride to 5 molar or yeah. Okay. So these are so-called the folding cores. Okay, now changes in the R2 that are happening are indicated there. The initial changes that happen here, delta R2 is small here. And then subsequently, these are followed by these green areas. First, it will fold into this, then this structure is formed, this induces the structure in this area, and then it follows in this manner. So the significance of that is indicated in this slide here. The top portion is completely unfolded, so there is substantial flexibility in the protein, multiple structures which are present, and now this is the initial folding course on the basis of secondary structural propensities. And as the folding transitions will happen, you see that this area gets folded. After that, this gets folded. And you see here, all of these stepwise folding events, they are very adjacent to each other, adjacent to the previously folded residues. What it means, a particular folded residue induces a conformational change into the neighboring residues. So kind of a cooperativity. All of this is shown on the folded structure, but these what we are observing will be on the unfolded state. Okay, but the neighboring residues are affected. The neighboring residues are affected, indicating there is a kind of a cooperativity in the folding pathway. What happened here?
Sir, when this quaternary structure, that means the quaternary structures are also formed during the folding stage only.
They are in equilibrium.
See, in this HIV, you have two proteins, na?
Yeah.
So they are happening together.
In the end, they will form together. In the unfolded state, they are separate.
They are separate.
They are separate. As you come closer and closer, that also will form.
Okay, so they will form together.
Together. Yeah. And there is a symmetry here.
Yeah, that's
These two are identical.
Yeah.
These two are identical. Okay, then you will see only one set of peaks.
Yes.
Because the two domains are identical.
Yes.
The two monomers are identical.
Yes. So that means you are actually making two tertiary structures together.
Yes. Dimer is getting formed.
Dimer is getting formed. So whole system is happening together.
And that's why you see it in these loops area. This is a loop which is holding it together.
Yeah.
And there's the interface here. This is holding it together.
Yeah.
And you see those ones happening systematically, stepwise. Hey, why this is not moving? Okay. So finally, after this is the finally folded state, the native state. And all of this is shown on the native state to show that there is a cooperativity, how it induces the structure in the neighboring ones, eventually to reach this state. So that is how the folding pathway can be identified. And once again, what is the problem? If I do it, then okay, this is the same picture which I shown you there. The folding initial preferences, these are called as the folding course. These are the areas which will get where it gets initiated, and then the folding transitions will happen in the nearby neighboring residues, and then it will show. The cooperativity shows pink, blue, green. Pink is the first one. Propensity gets initiated over there. After that, the blue will form, then the green. So therefore, stepwise, these are folding to form the final structure. Okay, now we can study protein folding by hydrogen exchange also. How do we study this? Consider this protein chain here, which is completely unfolded, and you exchange all the protons with the deuterium. All the protons are exchanged with the deuterium. Okay, therefore you see all D here, it is a completely unfolded chain. Now, we want to initiate folding. How do I get this the unfolded state? I might have done it by using urea or something, whatever, some denaturing agent, I might have put it there. Now you dilute in H2O, you add H2O to it, and dilute it in H2O. Okay, initially this is all D2O, and you dilute it in H2O and at low pH. Why do you at low pH? At low pH, the exchange rate is small. Therefore, I do not want them to exchange here, but I want to initiate the folding process. When I put it in D2O, in H2O, and I'm diluting it. When I dilute it, I'm providing a folding condition for the protein. So and when that happens, you will see some portion of the protein is folded at this point, but it is not exchanged because I'm putting the pH is low. So it is portion of the helix is formed here, but all of them are still Ds. Now what I do, I increase the pH. This is called the pulse labeling. Increase the pH. Increase the pH to 7. This is maybe like 2 pH or something like that. Okay. So, and increase the pH to 7 or something. That's called the pulse labeling. So you give a pulse of pH change. And then when that happens, the folding gets initiated, and the exchange gets initiated. Then ones which are on the surface of the protein here, they will get exchanged to hydrogen, H. Okay. And you give it for a certain time period, TF or something. TF2, you start here and then you give it for a period TP, then you stop labeling. That means you lower the pH again. This labeling here means deuterium is changed to proton. Deuterium is changed to proton. At TP you stop labeling, that means you lower the pH again. Suddenly you lower the pH. And after that you allow the protein to fold completely. Allow it to fold completely, and then you record this a 2D spectra, HSQC spectra. See, then you will see that the ones which is unfolded here, but these are all protons, this will actually fold into this state, and then you can see the chemical shifts of those in the HSQC spectrum. Here you look at this in the HSQC spectrum. Okay, these residues you can monitor, and because now it is stable. You're not doing anything, you're recording the spectrum, and you will see these peaks you will see, H protons you will see. Now if you do this for different time periods, different things will get. In other words, here, if you change this TP, then more of this will be labeled. Okay, then you monitor again. Therefore, you do it as a function of TP here. And so more and more residues will get labeled, and you can monitor those. The stepwise folding of the protein also you can monitor in this manner. Okay, so much for protein folding. You have used different techniques. Now I go into the even more, little bit more challenging systems, that is the NMR of large proteins and assemblies. So you consider a large protein or an assembly which is like this, a big thing which is formed here, and normally these ones are not observable. So in those, when you talk to the physicist, you can call this as a dark matter. Dark matter is, is not observable. You cannot see the dark matter. So you don't get a signal from there. Okay. And then in the NMR context, this kind of a situation, you can analyze it in terms of the line weights. What is the kind of a line weight with magnetic field strength? What you will have on the size of the protein. Here the plots are, these are calculated plots. 320 nanoseconds, 60 nanosecond, 20 nanoseconds. These are the correlation times. Correlation times is the protein tumbling. 320 nanoseconds means it is a very large system. Okay, very sluggish, very slow in tumbling. Okay, and 60 nanoseconds is smaller than that, and 20 nanoseconds is smaller than that. Typically, if you have a protein of, let us say, 10 kilodalton, and your correlation time will be approximately 5 nanoseconds. So therefore, these are already pretty big systems, but and they depend heavily on the molecular weight, of the protein. So this is the 320 nanoseconds. It is a huge, this will be megadalton size assembly. And this happens not for one protein. When a particular assembly is formed, then you will find this sort of a situation, and you can hardly see the signals there. So you look at the line weights, what happens here. If you have, and this is depend on the magnetic field strength. At about, suppose you have a 500 megahertz spectrometer, first this here, and if you have 320 nanosecond, what is the line width there? So it's somewhere here. Okay, so it's like about 40-50 hertz line width. And of course, if we increase the field, then this will come down here. At 1000 gigahertz, actually, we get a better line width over there. And 16 nanoseconds, it will be something like this. 20 nanoseconds like this. So if you have small protein, it really doesn't matter. We can measure at any of the magnetic field strengths. Otherwise, you have to measure at high magnetic fields for large proteins. And this is the result of an effect which is called as a TROSY, which I will explain in the next slide. Okay, and similarly for the N15, this is translated into the molecular weight here. So this is 800 kilodalton, this is 150 kilodalton, this is 50 kilodalton. Okay, so if we have 10 kilodalton, it will be much more flatter here in this kind of a situation. So in terms of the correlation time and in terms of the molecular weight, this is what it is. And when it's going down, this calculation is for what is the experiment which is known as TROSY. And TROSY, why does the line weight change here? This is because of a particular phenomenon known as the cancellation of the effects of dipolar relaxation and the chemical shift anisotropy relaxation. When the chemical shift anisotropy relaxation compensates for the dipolar relaxation, you start getting these smaller, narrower lines. And therefore, you have, and that is more effective at this field strength. So it's not effective at a very lower field strength. Neither it is much effective for lower molecular weight molecules. If you have large molecular weight molecules, then you have a higher magnetic field strength. Then you see the effect much more in a pronounced manner. And that is the TROSY experiment, which I was mentioning to you. This is attenuated T2 relaxation by mutual cancellation of dipole coupling and chemical shift anisotropy indicates an avenue to NMR structures of very large biological macromolecules. So this was published in 1997, and this, in fact, this was one of those main things which actually led to eventually the Nobel Prize to Wittrick. It's not only this, but the previous, of course, the NOA-based structure determination, etc., all of that was already there. But this actually provided a boost to much larger systems. And that I'm explaining here a little bit. The TROSY experiment, what it does is, if you have a HN correlation peak, okay, typically what if you're doing decoupling of the nitrogen 15 proton coupling, you will see one peak in the center. In the HSQC spectrum, you see one peak, right? There is no coupling anywhere. So in the normal HSQC spectrum, you'll have this. But if you don't decouple, both the amide proton and the N15 are doublets. Okay. And when that is the kind of a situation, this is like a cozy pattern. In the cozy pattern, you have this plus minus this kind of a situation, right? You have the 4 peaks over there. And the separation between them is the J coupling. Okay. Now, in the large systems and large spectrometer frequencies, all these 4 components do not have the same intensities. They have different intensities. The reason is these ones are governed by different relaxation processes. To some, there are 2 relaxation phenomena, as I mentioned, dipole coupling relaxation phenomena. There is also chemical shift anisotropy relaxation. You saw that in the R2 expression. R2 expression, which you gave earlier yesterday, in the heteronuclear R2 expression, you have the C square and the chemical shift anisotropy contribution there. And the D square was related to the dipolar coupling relaxation. And the 2 things work in opposite directions. And they tend to cancel each other. And this cancellation is maximum at 1 gigahertz. So you see that 1000 megahertz, that is 1 gigahertz. And that is cancellation is maximum at that point. And that happens differently in different components. It is in one component which is maximum, and that component will become very narrow. And all other things will disappear. If you decoupled that, then of course you will find one peak at the center, which has the line width from all the contributions, and that will be a broad signal. The normal HSQC. I will show the effect of that here. See, this is the normal HSQC peak, and this is the TROSY peak. See, these 4 components which are there, they have different line weights and different intensities. If you did a TROSY experiment, you get this peak only. This peak has the highest peak intensity, that is, this retains this one, it just eliminates all of those ones. Although this peak will not be at the chemical shift position, it will be at a slightly shifted chemical shift, but that is no big deal. You can always adjust that chemical, because the coupling constant is known. NH coupling constant is known, it is about 100 hertz. It will be shifted by 50 hertz. So it doesn't matter. See, it's indicated here, minus 50 plus 50, this is the 0, this is the center. So therefore, there is no big deal. So you get a very narrow line here. You compare to this, what is this peak? You compare this peak and this peak. This is very narrow and intense. Intensity is also higher. Therefore, when large systems you are considering, you will have a very sharp line coming in if you do a TROSY experiment. You will see the effect of this in the next slide. And this is the normal COSY, or the COSY means HSQC spectrum. This is HSQC spectrum, and this is the corresponding TROSY spectrum. See, these lines have become very, very sharp here. This is because we picked up that particular component. And this is indicated by taking the cross sections here. This is the COSY cross sections, or the HSQC. Wittrick used to call it as he likes to call it as COSY. Okay, but these are HSQC, these are HSQC spectra. And a particular residue, for the Z residue R90, this is in the COSY, this is in the TROSY. L64, L64. E119, E1. Look at this intensity change. Enormous change. Similarly here. Similarly for the nitrogen, this is for the proton. And this is for the nitrogen. Because you measure the line width along this axis or along this axis. Both you can measure, no? So if you measure along this axis, that is a nitrogen line width. If you measure along this axis, horizontal line axis, it is a proton line width. Vertical axis, it is a nitrogen 15 line width. In either case, you see big increase in the big enhancement in the signal intensity. The lines is sharpened quite substantially. Of course, you see a small chemical shift difference here, and that is because of what? That is because of that 50 Hertz suppression. And you see here, this is even larger protein system. This is about 130 kilodalton protein. And this is the normal HSQC. And look at this, TROSY. It's a phenomenal improvement in the line weights by doing this relaxation optimized experiment. And remember, this will only work if you are working with large proteins. Okay, if you are working with a 10 kilodalton or 5 kilodalton, no point. You are actually wasting time. If you do that, there is no significant improvement in any of the 4 components of the 4 peaks. You don't need to decouple. Then you can decouple better, you get a better intensity. In a large system and at a higher magnetic field, you will get this. Only the idea here was to go to larger and larger protein systems. And that normal HSQC will not help you there. This is very difficult to analyze. Therefore, you do this development, then you have this very short peak that can actually analyze all of this. And you can do even better, which is making use of the inept sequences there. We will not go into that. I will only show you the results here. And this is the complex here, GROEL-GROES complex. This is the chaperone, protein chaperone. What is the size of this GROEL-GROES complex? 900 kilodalton. Now, this whole thing, this from here to here, this is 900 kilodalton. This is the same as this one here. The assembly of this was known. Okay, this crystal structure is determined of this. So this assembly is known. This consists of repetitive multiple units of the same protein. And the same thing is indicated. There are 2 domains here, the SR1 and there's the other domain which is present here. And this consists of, you can, this 472K and SR1, this is another one which is around 500. So totally approximately about 900 kilodalton. And there is one here, there is a 72K. 72K and no, this one is 472K and this is 72K and this one is another one which is the remaining. So you have a total of 900 kilodalton. This 72K system, this consists of 7 units of one protein chain, which is 10 kilodalton. They are all assembled into a systematic manner, symmetrical manner to form the 72K assembly in this. So this is 10K protein, 7 units of that assembled in a particular manner to form this. This is what you will see in kinds of, in viruses, for example. You will see such kind of things happening. But you are seeing that here as well. Now, in this situation, one was able to see in the TROSY for this peak 72K system here, you were able to see in the peaks in the TROSY experiment. And in the crypt TROSY modification, you see many more peaks. And once you add this SR1 to this, okay, you see nothing here. But in this one, you still see several of those. So this is a further enhancement. This is called a polarization transfer, TROSY. Inept sequence is used. Crypt and CRENEPT, these 2 different sequences are used. And that actually leads to a better sensitivity here. You can observe more signals into this. So here the target is to obtain first the proper signals which can be identified to individual residues, and you will be able to see the different assemblies. Okay, now this is general indicator as to how much you can go with what kind of a spectrometer frequencies, what size of proteins you can go, and what sort of NMR experiments one has to perform. See, magnets 500, 600, 800, 900, 1 gigahertz. And what is the molecular weight size you want to go study with that? 10, 25, 35, 50, 100 kD. And then, of course, that was an extreme one, which was 900 kD. And what are the experiments you will do? Of course, cryoprobes are here in 500 and 600, 700 and 800. They are not there for the, well, they are also there for the 800. And NMR in this molecular range, if you want, you can do 2D. If you are in this range, you need 3D and 4Ds. Once you come here, then you require TROSY. Along with that, you also need triple resonance experiments, pulse field gradients. Then, of course, these are all other strategies which one is used, RDCs, CCR, okay. And what are the requirements of the proteins? You need, for such a small protein, you don't need to do any, you can do proton experiments, you don't need to do anything else. So C13, N15 experiments you can do, okay. And then deuterium C13 or deuterium labeling is also required, because deuterium labeling will reduce the line weights. Further, it will narrow down the line weights, because the aeromagnetic ratio of deuterium is 1/6 of that of proton, and the line width will also be dependent on the deuterium. So therefore, that relaxation will also help you to sharpen the lines. Then you segment the labeling, and okay, those are techniques. Now I come to another even more important, even greater system, which is the dynamin and endocell, functional significance here. Now here is a system which is, there is a protein budding clathrin coated vesicle, and if something has to be internalized, there is a protein which is called as dynamin. So this molecule has to be internalized into the cell, okay. So when that has to happen, there is a protein called dynamin which actually wraps around this neck of this, forms a big rope here, and with GDP hydrolysis, this will get cleaved, and then the thing is internalized. After this is gone, this is what happens. Okay, dynamin forms a neck with GDP hydrolysis, this will be relieved, and then the molecule is internalized. Now, what is this dynamin? Once again, something is not moving. So the dynamin is actually a small protein. It is about 864 residues. It contains these many domains. GTP is 316. Okay, and this particular domain which is here, this is the one which is responsible for the self-association of this dynamin. And what will be the molecular weight here? 864 residues. Okay, 10 kilodaltons is about, let's say, about 100 residues. Okay. Now 800, 100, 890, the 10 about it will be about 100 kilodalton, roughly 100 kilodalton this will be. Okay. But when this forms a rope along the neck of this one, this will have the size of several megadaltons, 20, 30 megadalton size. So this will form, this will self-assemble into a large system to find a rope. And is it possible to study this? Well, what is known about this system? The structure of this is known. Structure of this is known, and nothing is known about the GED. But this is the domain. If you chop off, it will not form an assembly. It will not assemble into the rope kind of a structure. Therefore, this is the crucial thing which is responsible for the assembly of the dynamin into a large rope. Okay. So therefore, this was the work of one of our students, Chuk. He is now a faculty in ISER Pune. So he expressed this particular domain of this protein in the HSQG, and this is 136 residues, and you expect a number 132 peaks. But what you saw, you only saw 26 peaks. So everything else is formed in the format of an aggregate, in the format assembly, large system it has formed. A big dark matter, as I said, but certain section of the protein is still flexible, and those 26 residues you are able to see. TROSY HSQC without decoupling or deuteration did not produce any more peaks. It did not help, because this size has become far too large for any of those things to work. So therefore, what has to be done here? So therefore, we adopted a particular strategy here to understand the association process of this protein into this. What you do, this is the kind of a system we are getting after we express the protein and you get this. Now we dissociate it by using urea. Then you get a monomer here. But the monomer, of course, also has lost its structure. It doesn't have a structure anymore. You dissociate it, but you can see the signals because all of these are monomers now, and you can see the signal, the protein monomer. Now we reconstitute this by stepwise slowly changing the conditions. And when you do that, you can monitor the association process of these individual monomers into this large assembly. And that is seen here. This is using guanidine hydrochloride. 6 molar guanidine hydrochloride, you see all of them. All the 136 peaks you see. You go to 4 molar, some things have gone. For example, this fellow has gone. Okay, and others have become weaker. All of these peaks are similar intensities. Now you see they are become weaker and some of them broadened out. And go to 2 molar, many more have gone. 0.5 molar almost has come close to this 0 molar one. See, all of the other ones have gone. This is the N15. Now what you can do, you can monitor the changes in the spectral patterns and identify which portion of the protein is folding first, which is going, or folding and associating. Remember, it is folding and associating. Both are happening at the same time. Okay, so therefore, you use this technique. To find out the folding, you use the circular dichroism. And to find out the folding pathways, you use the R2s. R2 measurements are telling you the changes in the motional characteristics, and which is undergoing chemical exchange. R2 is increasing. Okay. Now here it is a 6 molar guanidine. The CD shows that, okay, there is no structure there. And you see very kind of a bell-shaped thing, which is typical for any unfolded protein. All the R2 values are roughly the same, not very different. Now you reduce it to 4 molar. This fellow has taken a slight dip. The helix is not formed yet. But this portion of the protein chain has vanished. Signals have gone. They have disappeared. They have already aggregated. This portion of the protein has aggregated. It has some small things may have formed. Helix is not formed yet. This is slowly changing the CDs. And this portion of the protein has gone. This also has gone. At the same time, you see these ones have gone up. These R2s have gone up. What does that mean? It indicates that when you go to next, these also have gone up. These ones have gone up. When you go to 2 molar, these ones go up even more, and all of these vanish. Now we go to 0.5 molar, all these ones have gone, they also vanished. So stepwise you can see the R2 when it is increasing means the line is getting broader, right? If R2 is increasing, the line is getting broader. So it is getting ready to aggregate. Stepwise they are getting ready to aggregate into a larger assembly. And what is the size of this aggregate? It is almost 10 megadalton. Between 5, there is a variation of 5 to 10 megadalton. You monitor the size by doing hydrodynamic gradient measurements using light scattering experiments. You cannot do that by NMR. You use light scattering experiments to determine what is the size of this protein assembly. So typically it was about 5 to 10 megadalton size. And you see, and then at 0.5 molar, this fellow still remains open. So in the assembly also, aggregated species also, this is still flexible. Now you see the helix is formed. Here also helix is formed. Okay, this going down here is an indication of the formation of the helix. Okay, and here the helix is almost completely formed here. So this is the normal native state kind of a pattern what you get here. And this portion and this portion are roughly the same, although this was the slightly more intensity. So stepwise you can see the formation of the helices, the progression of association as you go from 6 molar to 0 molar. Initially these peaks have vanished, and these a little bit here and there have vanished. This induces the association into the next ones, and so these ones have vanished stepwise. And you go to 0.5 molar, the helices are formed. So you look at these are the helices. You have 2 helices, there is a loop here. So this consists of 2 long helices and 1 alpha. This you get it from secondary structure predictions. You can see what are the helices and this is a completely unfolded state. And these are the ones where we are seeing the signals. even after the association is formed, these helices are formed, these helices self-assemble among themselves, but this portion remains flexible still. Okay, so therefore, the C-terminal half of alpha 1 and alpha 2 are nucleation sites for association. Helix formation precedes association. Association of helices and intermediate exchange leads to disappearance of peaks. And that is shown here in this manner. The way the helices are getting formed, and as you change there's a flexibility there's a complete association, dissociation dynamics going on here. And as you go down into the guanidine concentration, more stable helices are formed and they assemble. They assemble to form a stable structure. And the schematic is indicated here. And these ones are oriented in opposite directions because of the charge complementarity. So if you look at this chain here, there is a charge complementarity of the molecules. Therefore, the chains, two chains running in opposite directions will actually associate. And therefore, when this process goes on, you form a kind of a rope. See this one rope, this red one fellow is increasing. This is forming the helices that are the packed in the middle, and you have these terminal loops which are hanging around. So these are flexible, and these are peaks which you are seeing. And what is the role of this? These ones actually wrap around the neck of this vesicle, budding vesicle, and this is the core of that rope which is getting formed. This is all full of these helices and forms a large assembly. Okay, protein dynamics and function. Well, this is only one slide I have here. HIV protease dynamics. How is it related? How dynamics is related to function? This is the active site of the protein where the other things will come and sit here, and then after the cleavage, these loops open up, flaps open up, and the chain will be thrown out. Therefore, it is necessary for this to be dynamic, so that to let in something after the reaction is over, it has to be thrown out. So this dynamics plays a crucial role. What happened here? Okay, this was the, okay, you go to this slide, yeah. And then I show another example of dynamics, the role of dynamics in protein function. This is one molecule which is called as a dynein, DLC8 protein. DLC8 protein is present as a cargo trafficking molecule. This whole thing, this is the tubular microtubule, and plus end to the minus end here. This whole system carries a cargo from one end of the microtubule to the other end of the microtubule. In that one, there is a small protein here, DLC8, which is responsible for attaching itself to the cargo molecule. Okay, and this once when it binds here, when it shifts to another place, it releases it. See, look at here. This is the way it is. It is moving, then actually, and then it slowly goes to another place and releases it. And you look at that in a magnified manner here. This is a dimer. This protein exists as a dimer here. This is a small protein. It's not a very big protein. This is a pH7. This is a dimer here, and the cargo binding happens at the center here. This is the cargo binding site. Okay, at pH 7 it is a dimer, at pH 3 is a monomer. That means if you reduce the pH, it actually equilibrium shifts towards the monomer. There is an equilibrium between monomer and dimer, and as you reduce the pH, it will shift to the monomer side. Okay, now that is schematically indicated here. A dimer interface, this is where the cargo is. So we did this experiment using a particular small peptide as a cargo to show what is happening. And initially, first we determined the dynamics of this protein at pH 7 and pH 6. pH 6, the dynamics is increased to many residues. Here it is restricted to a few residues, and then it's increasing to more residues as you go down to pH 6. And what is the consequence of this? This is the binding experiment with a particular peptide. Okay. Now here you see when you add that peptide, DLC8 dimer, you have all these 4 residues. Okay, and then we add the peptide at pH 7, see what is happening. So this peptide, this peak is getting shifted to this place as a result of the interaction. Okay, and similarly this peak is getting shifted here. I only marked a few of those. This peak is getting shifted to here. There are other movements also, because these are very distinct. You can monitor, you can easily see it. Now to the same situation, now you reduce the pH to 6. See, now this fellow comes back here. Portion of this comes back here. Okay. And that means that this particular portion of the protein is now actually getting released. Okay, so therefore, that is what I said, the pH switch therefore now appears as a trafficking mechanism. Peptide binding is compromised here. So at particular pH, it binds the peptide, and if you change the pH at some other place, it will release the peptide. So this is a kind of a signal. pH change can be a signal for the trafficking mechanism. So therefore we call it as a pH switch for cargo trafficking. Okay. I think that is the end. So we have covered a lot in this series, all the way from structure, dynamics, and the functions. Folding, everything is done. So we have sort of completed the most modern applications of NMR in biomolecular systems. So with that, we come to the close of this.
Those over, if they have any doubt, no, they should
Yeah,
say.
if you have any questions, we can ask.
Questions and also.
Any doubts?
Any doubts, they can contact by email.
Any doubt, ask or ask by email. No, any doubt, a client दे दो.
Any doubt, please ask. Yes.
ये डाल दो पहले.
Yes.
And then finally तुम लिखो. You may contact Professor Ashur through email. You may also contact.
खाली तो opposite email also.
You may also.
Okay. You may contact Professor Ashur
By email.
by email. By email.
Sir, you just spell your email ID here.
Sir का email ID.
No, sir, I've typed it. Huh?
I've typed here?
I've typed. It's high, no? It's a good. थोड़े लाइट में डाल दो उसको. क्या हो गया?
ठीक है.
Okay, so I think
Yeah.
I hope you all enjoyed it, all the students and whosoever is there. So I wish you all the best. You want to continue work on proteins, proteins and nucleic acids. You have to read this, listen to these lectures again and again and again and again, several times, because there is so much material, so much stuff,
Yeah, so much things to be learned. Actually.
so much things to be learned. Yeah.
Well, participants, I think with this, Professor Hosul completes his part. So next week, a break for you to recapitulate all the things available in the this one or with the site, revise all this, and then next week we'll be starting this
September.
MRI part.
September.
MRI part.
From September?
So next week is a free time for you. No, not exactly. You revise all the things. Okay, so you can start.
Clear your doubts, that's all.
And in between, any doubt,
Assignments they should do also, no?
Yeah.
yeah,
assignments
in
also.
between you solve this assignment is already uploaded, and contact Professor Hosul if you find any doubt or anything, any explanation or anything, you can just contact.
Yes, sir, very tough.
Try. You read to
It's very tough.
try once or twice. Materials are available. I think you can understand what exactly it is going, how it is happening, right? Anyway, all the best.